November 1944, somewhere over the Ardennes Forest. Lieutenant Robert Harmon's P-47 Thunderbolt shuddered violently as cannon shells tore through the fuselage. Metal fragments exploded inward. The instrument panel shattered. Hydraulic fluid sprayed across the cockpit glass. Oil temperature gauges spun wildly before going dark. Harmon felt impacts rippling through the airframe like a jackhammer against steel. He counted them instinctively. 10 hits. 15. 20. The aircraft kept flying. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow, I've saved something extra special for you. German pilots pulled away, certain they'd scored a kill. They'd seen pieces breaking off. They'd watched smoke trailing from the engine. Standard doctrine said any fighter absorbing that much damage was finished. They turned toward easier targets, expecting to see a parachute blossom or wreckage spiraling earthward. Instead, Harmon's Thunderbolt maintained altitude, wings level, propeller still turning. He nursed the throttle, felt the controls respond sluggishly but consistently, and pointed the nose toward home. 40 minutes later, he touched down at his base in Belgium. Ground crews counted the damage. 207 holes. Cannon strikes, machine gun punctures, shrapnel tears. The rudder was shredded. One aileron hung by its hinges. The tail section looked like it had been hit with a shotgun blast at close range. Fuel tanks were perforated. The engine cowling was missing entire panels. Yet every critical system had continued functioning. The engine had run. The controls had worked. The pilot had survived. This wasn't an isolated incident. Across the European theater, similar reports accumulated in squadron operations logs. Thunderbolts returning with damage that should have been catastrophic. Aircraft that should have disintegrated, landing safely. Pilots who should have been casualty statistics, walking away. German intelligence officers began documenting a pattern they couldn't explain. The American Republic P-47 refused to die. The mystery had roots that predated the war entirely. Engineers at Republic Aviation Corporation hadn't set out to build the most survivable fighter aircraft in history. They'd been trying to solve a completely different problem. When the Army Air Corps issued specifications for a new pursuit fighter in 1940, the requirements emphasized firepower and range. Speed and altitude performance mattered. Maneuverability was essential. Survivability was mentioned, but only in general terms. Armor protection for the pilot. Self-sealing fuel tanks. Standard defensive measures that every modern fighter incorporated. Nothing revolutionary. Republic's design team, led by Alexander Kartveli, approached the project with engineering pragmatism rather than aesthetic ambition. The result was an aircraft that looked wrong to almost everyone who saw the early prototypes. It was enormous for a single-seat fighter. The fuselage was wide and deep. The engine cowling bulged dramatically. Empty weight exceeded 7 tons. Critics called it ungainly. Some called it grotesque. Test pilots called it the Jug, short for Juggernaut, a nickname that acknowledged both its size and its ponderous appearance. The name stuck, but it carried an unintended compliment. Juggernauts were unstoppable. What those early critics missed was structural philosophy embedded in every rivet and bulkhead. Kartveli's team had designed the P-47 around the Pratt & Whitney R2800 double Wasp engine, an 18-cylinder radial power plant that produced 2,000 horsepower. That engine alone weighed over a ton. Supporting it required a fuselage structure built like a bridge truss, not a lightweight racing frame. The engineering solution produced massive structural members. Wing spars were thick rolled steel. Longerons ran the length of the fuselage with cross-bracing every few inches. Skin panels were heavier gauge aluminum than competitors used. The aircraft wasn't just big. It was dense with structural material. Republic's engineers justified the weight with performance requirements. The turbo supercharger installation needed space. The intercooler required ducting. .850 caliber machine guns with ammunition boxes demanded room in the wings. The fuel system with self-sealing tanks and multiple compartments added complexity. Every component needed robust mounting points. The accumulation of necessary structure created an airframe that was, almost accidentally, extraordinarily difficult to destroy. Early production models began reaching operational squadrons in late 1942. Initial combat reports from the Pacific and European theaters focused on performance characteristics. The P-47 was fast in a dive. It was stable at high altitude. It could absorb battle damage and continue flying, though this last observation appeared almost as an afterthought in early assessments. Then combat intensity increased. Fighter sweeps penetrated deeper into enemy territory. Bomber escort missions stretched into the heart of Germany. Ground attack operations put aircraft into the teeth of flak concentrations. The tempo of operations accelerated, and the P-47's hidden advantage became impossible to ignore. Aircraft were returning from missions that should have been fatal. Squadron commanders began requesting detailed damage assessments. Maintenance officers photographed destroyed components that had somehow kept functioning. Intelligence sections compiled reports of multiple aircraft returning with hundreds of bullet holes. January 1943, Debden Airfield, England. Technical representatives from Republic Aviation arrived to investigate recurring reports of extreme battle damage survival. They weren't responding to a mechanical defect. They were trying to understand why P-47s kept flying when the laws of aerodynamics and structural engineering said they shouldn't. The representatives interviewed pilots and examined damaged aircraft. They studied bullet trajectories through wing structures. They analyzed how cannon shells had passed completely through fuselage sections without severing critical control cables. They documented hydraulic lines that had been cut but maintained enough pressure for the pilot to lower landing gear. They photographed electrical systems that continued operating despite having wiring harnesses partially destroyed. What emerged was a picture of redundancy that hadn't been deliberately planned but resulted from design choices made for other reasons. The fuselage structure was so overbuilt that severing one or even several longerons didn't compromise overall strength. Control cables were routed with enough separation that battle damage rarely cut all cables to a single surface simultaneously. The radial engine, with 18 cylinders arranged in 2 rows, could lose multiple cylinders and continue producing usable power. One pilot had returned to base with 5 cylinders completely destroyed. The engine was running rough, overheating, losing oil pressure, but it was running. Ground crews found pieces of piston embedded in adjacent cylinders. The connecting rods were bent. Somehow, enough compression remained in the surviving cylinders to sustain combustion. The pilot had flown 90 miles back to friendly territory with an engine that should have seized within minutes. Republic's engineers examined the wreckage with professional fascination. This wasn't theoretical damage tolerance being discussed in a conference room. This was empirical evidence of survival beyond design specifications. They began systematic analysis of every returned aircraft with significant battle damage. Photography documented each impact location. Draftsmen created detailed drawings showing trajectory angles. Metallurgists examined how aluminum skin panels had torn versus punctured depending on projectile velocity and impact angle. Patterns emerged. German 20mm cannon shells, the standard armament on Focke-Wulf 190s and Messerschmitt 109s, typically created fist-sized holes in aluminum skin. If they struck structural members, they often passed through without detonating. The P-47's heavy gauge structure was thick enough that contact-fused shells sometimes didn't receive enough resistance to trigger detonation. They punched through and exited the far side, leaving large holes but no explosive fragmentation damage. Machine gun rounds, smaller and faster, created different damage signatures. They perforated skin panels but rarely destroyed structural members unless they hit directly on. The P-47's densely spaced internal structure meant that most machine gun fire hit non-critical areas. Fuel tanks, control surfaces, engine accessories, these took damage routinely. But the core structure, the pieces holding the aircraft together, proved remarkably difficult to destroy. One aircraft returned from a mission over France with 63 documented hits. Ground crews removed panels and found 14 additional impacts that hadn't penetrated the skin completely. The pilot reported normal control response throughout the engagement and return flight. Engineers studying the damage found that most hits had struck areas between structural members. The few impacts on spars or longerons had caused localized deformation but no fractures. The aircraft was repaired and returned to service within 72 hours. Replacement skin panels, new hydraulic lines, patched fuel tanks, and it was operational again. The documentation process became standardized. Every aircraft returning with significant battle damage received a comprehensive inspection. Maintenance officers filled out damage assessment forms listing each impact location, the type of damage, which systems were affected, and whether the damage compromised structural integrity. These forms were collected at group level, then forwarded to higher headquarters. By mid-1943, Air Material Command had accumulated hundreds of detailed damage reports specifically for the P-47. Statistical analysis began revealing quantifiable survivability advantages. P-47 squadrons had lower loss rates per sortie than units flying other fighter types in similar missions. Pilots flying Thunderbolts had higher survival rates when shot down over enemy territory. Aircraft damage rates were actually higher for P-47s, meaning they were getting hit more often, but loss rates were lower. They were absorbing damage that would have destroyed other aircraft. Republic's engineers cross-referenced this data with design specifications. The correlation was clear. Structural members designed to handle 9G maneuvers with safety factors of 50% were vastly overbuilt for normal flight loads. That overdesign created immense damage tolerance. Wings stressed for 12G ultimate load could lose significant structure before failing. A longeron designed to carry 8,000 pounds of load could be partially severed and still carry 4,000 pounds, more than sufficient for steady flight. The engine installation, criticized for being heavy and complex, dispersed impact damage across multiple systems. Turbocharger hit. Engine keeps running. Oil cooler destroyed. Temperature rises but remains manageable long enough to reach friendly territory. Intercooler punctured. Performance degrades but aircraft remains controllable. February 1943, North Africa. The 79th Fighter Group began combat operations flying P-47s in support of ground forces. The desert environment introduced new damage sources. Sand ingestion. Extreme temperature cycling. And a dense concentration of anti-aircraft artillery protecting axis positions. Flak damage proved different from air-to-air combat damage. Anti-aircraft shells created larger, more random fragmentation patterns. A single 88mm shell burst could send dozens of fragments through an aircraft. Each fragment had different mass, velocity, and trajectory. The result was widespread damage across large sections of airframe. One P-47 flew through a flak burst that shredded the entire right wing trailing edge. Aileron cables were cut. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. Hydraulic lines were severed. The aileron itself was hanging loose. The pilot had no right aileron control whatsoever. He compensated using left aileron and rudder, creating cross-control inputs that induced roll. It was inefficient, exhausting, and it worked. He landed successfully. Another aircraft took a direct hit to the fuselage just behind the cockpit. Fragments penetrated the radio compartment, destroyed communication equipment, severed multiple control cables, and perforated 2 fuel tanks. Fuel streamed from the holes. The pilot shut off flow to the damaged tanks and switched to reserve. Fuel quantity dropped to 15 gallons. His base was 40 miles away. Fuel consumption at cruise power was roughly 1 gallon per minute. He throttled back to minimum sustainable power, reduced airspeed to just above stall, and calculated he'd run dry 5 miles short. He made it with the fuel gauge reading empty. Ground crews found less than 2 gallons remaining when they drained the tanks. That same aircraft had control cable damage that gave the pilot only 60% elevator authority. He couldn't pull the nose up aggressively. Landing approach required a shallower glide path and higher speed. He touched down 20 miles per hour faster than normal, used every foot of runway, and stopped with yards to spare. The accumulation of these incidents changed pilot psychology. Confidence in the aircraft grew with every improbable survival. Pilots began pushing mission profiles further. They accepted assignments that would have seemed suicidal in lighter fighters. Deep penetration strikes into heavily defended areas. Low-level strafing runs against flak-protected targets. Extended combat air patrols with minimal fuel reserves. The aircraft's reputation became self-reinforcing. Pilots believed it would bring them home. That belief encouraged aggressive tactics. Aggressive tactics produced results. Results justified the confidence. German pilots noticed the pattern. Luftwaffe intelligence officers collected combat reports describing P-47s that refused to go down despite concentrated fire. Experienced German fighter pilots, men with dozens of kills, reported emptying entire ammunition loads into Thunderbolts without achieving catastrophic damage. Some attributed it to American armor protection. Others speculated about secret structural materials. The reality was more prosaic. Simple overbuilding combined with redundant systems created survivability through brute force, not clever engineering. There was no secret. The P-47 was just massively, excessively strong. March 1944, England. A new study began examining the relationship between aircraft weight and combat survival. Analysts compared loss rates across all American fighter types operating in Europe. The P-47, heaviest of all single-seat fighters, had the lowest loss rate per 100 sorties. The P-51 Mustang, lighter and more agile, had higher loss rates in comparable missions. The correlation held across different mission types. Bomber escort, fighter sweep, ground attack, in every category, the heavy Thunderbolt lost fewer aircraft per sortie than lighter fighters. The conclusion challenged conventional wisdom. For decades, fighter design had emphasized lightweight for maneuverability. The P-47 succeeded by inverting that logic. Mass provided protection. Structure provided resilience. Republic Aviation published internal design studies exploring the phenomenon. Engineers calculated that increasing structural weight by 1,000 pounds reduced catastrophic failure probability by approximately 30%. The relationship wasn't linear, but it was consistent. Heavier structure absorbed and dispersed impact energy more effectively than light structure. This wasn't revolutionary physics. It was straightforward mechanics. But applying it to fighter aircraft contradicted every design trend of the previous 20 years. The P-47 had stumbled into a survivability advantage by accident. Designs intended to support a powerful engine and heavy armament had created an aircraft that could absorb punishment far beyond its design specifications. Now that advantage was being documented, quantified, and analyzed for future application. April 1944, operational training units across England and North Africa received updated pilot training materials. New sections addressed battle damage management. Pilots learned what systems could fail without preventing safe return. They learned compensation techniques for lost control authority. They learned emergency procedures for hydraulic failure, electrical failure, partial engine failure, and fuel system damage. The curriculum emphasized one principle. The aircraft will keep flying. Your job is to keep it pointed toward home. Real combat examples illustrated each lesson. A pilot who'd lost his entire vertical stabilizer to flak and compensated using differential throttle. Another who'd flown 40 minutes with no instruments after his panel was destroyed. A third who'd landed with one main landing gear extended and the other jammed retracted, dragging one wing on the runway until the aircraft ground looped to a stop. All had survived because they'd kept trying. The aircraft had given them that opportunity. Training officers emphasized the psychological component. Panic killed more pilots than mechanical failure. Pilots who gave up when they saw damage often bailed out of aircraft that were still flyable. Pilots who stayed calm, assessed the situation, and worked the problem usually made it home. The P-47's reputation supported that mindset. Knowing the aircraft was tough encouraged pilots to stay with it. That encouragement saved lives. Statistical evidence backed the training emphasis. Of all pilots who bailed out of P-47s over enemy territory, subsequent investigation revealed that approximately 40% had abandoned aircraft that were still controllable. They'd seen damage, assumed the aircraft was doomed, and jumped. Analysis of recovered wreckage showed these aircraft likely could have returned to friendly airspace. The pilots had underestimated their aircraft's capability to survive. May 1944, the skies over Berlin had become a crucible where engineering theory met violent reality. Captain Thomas Ridgway led his flight through heavy flak concentrations protecting the Reich's capital. Black puffs of exploding shells created a lethal maze. Fragments zinged through the air at supersonic speeds. One burst detonated 15 feet below Ridgway's aircraft. He felt the impact ripple through the fuselage before he heard it. The control stick lurched in his hand. The aircraft yawed hard right. He fought the controls, applying left rudder pressure. Response was mushy but present. Something had been severed or damaged, but the aircraft was still responding to inputs. He called for a systems check. Oil pressure normal. Engine temperatures climbing but within tolerances. Fuel flow steady. Hydraulics showing reduced pressure but still functional. He worked the stick through its full range of motion. Elevator response was sluggish. Aileron control felt loose. The rudder had partial authority. None of it felt right, but all of it worked. His wingman pulled alongside and visually inspected the damage. The report came back terse and grim. Your entire left horizontal stabilizer is shredded. I can see through it. You've got about half your rudder missing. There's a hole in your fuselage I could climb through. Ridgway acknowledged the report and made his decision. He was staying with the aircraft. Berlin was 120 miles from the nearest friendly airfield. At cruise speed, that meant 25 minutes of flight time. 25 minutes nursing a crippled fighter through hostile airspace while German interceptors hunted stragglers. He reduced power slightly to ease stress on the damaged structure. Airspeed dropped to 280 miles per hour. The aircraft felt like it was fighting him with every control input. He had to lead every turn by several seconds. Banking left required right stick initially to overcome adverse yaw, then hard left rudder to complete the turn. It was exhausting and imprecise, but it worked. German fighters appeared at his 6 o'clock. His wingman called them out. 2 Focke-Wulf 190s, diving from altitude. Standard bounce tactics. Ridgway's damaged condition made him easy prey. His wingman broke hard left to engage. Ridgway kept his course steady. He couldn't maneuver aggressively without risking structural failure. The Focke-Wulfs opened fire. Tracer rounds arced past his canopy. Impacts stitched across his right wing. More holes. More damage. He felt the airframe shudder but maintain integrity. Return fire from his wingman drove one German fighter into a defensive break. The second made another pass. This time rounds tore through Ridgway's engine cowling. Oil pressure began dropping. Cylinder head temperature spiked. The Pratt & Whitney R2800 was taking damage. 3 cylinders lost compression almost simultaneously. The engine began running rough. Power output degraded noticeably. Airspeed bled off. 260 miles per hour. 240. Still flying. Still controllable. The Focke-Wulfs broke off. Either they were low on fuel or ammunition, or they'd assessed Ridgway as doomed and not worth pursuing. His wingman rejoined on his wing. 20 minutes to friendly territory. Oil pressure continued falling. Temperature continued rising. Ridgway enriched the mixture slightly, trying to cool the engine. The rough running smooth marginally. 15 cylinders were still firing. 15 out of 18 was enough. The aircraft droned westward. Every minute felt like an hour. Control response continued degrading as aerodynamic forces worked on damaged surfaces. The missing rudder section created asymmetric drag. He had to hold constant right rudder pressure just to maintain heading. His leg cramped. He ignored it. 10 minutes from the border, the oil pressure gauge hit 0. The engine was running dry. Friction began generating heat faster than airflow could dissipate it. Bearing temperatures soared. Ridgway knew he had minutes before seizure. Maybe less. He pushed the mixture to full rich, trying to use fuel as a coolant. It helped marginally. The engine kept turning. 8 minutes out, smoke began trailing from the cowling. Not heavy black smoke indicating fire, but gray-white vapor suggesting oil burning off hot metal surfaces. Still no flames. Still producing power. 6 minutes out, the engine temperature gauge pegged at maximum. The needle couldn't go higher. Actual temperature was unknown but certainly beyond safe limits. Metal was expanding, tolerances were disappearing, and still the pistons rose and fell. Still the propeller turned. Still the aircraft flew. For minutes from the border, his wingman reported visual contact with friendly fighters. Allied Spitfires on patrol. Ridgway rogered the call but kept his focus on flying. Every control input required full concentration. The aircraft wanted to roll right and yaw left. He countered with crossed controls, creating a flight profile that was aerodynamically ugly but functionally stable. 2 minutes out, he crossed into Allied airspace. The engine was making noises no engine should make. Metallic grinding. Sharp knocking. Deep rattling. Components were failing internally. The propeller continued rotating. 1 minute to the nearest emergency landing field. Ridgway called the tower. Emergency landing. Battle damage. Possible engine failure on approach. Tower cleared all traffic. Crash crews stood by. He entered the pattern at pattern altitude was impossible with his damaged stabilizer. He stayed low, extended downwind, turned base, then final. Landing gear extended with a hydraulic groan. Green lights confirmed. Flaps down. Airspeed 85 miles per hour, barely above stall. The aircraft mushed toward the runway. He added power. The engine coughed, stumbled, then responded. Propeller RPM fluctuated wildly. 50 feet. 30 feet. 10 feet. The main wheels kissed concrete. He held the tail up as long as possible, then let it settle. The tail wheel touched. He was down. He rolled out, applied brakes gently. The aircraft slowed and stopped. Only then did the engine cease. The propeller froze mid-rotation with a sound like a hammer striking an anvil. Silence. Ridgway sat in the cockpit, hands shaking from exertion and adrenaline. He'd flown 25 minutes on a disintegrating aircraft with a dying engine. The P-47 had carried him home. Ground crews swarmed the aircraft. The damage assessment took hours. They counted 412 separate impact points. Some were small-caliber machine gun rounds. Others were cannon shell fragments. Several were complete 20mm shells that had passed through structure without detonating. The left horizontal stabilizer had lost 60% of its surface area. The rudder was half gone. The fuselage had 3 major penetrations large enough for a man to fit through. The engine had taken 17 direct hits. 5 cylinders were destroyed. 2 connecting rods were cracked. The crankcase had a fissure leaking oil. The oil cooler was punctured in 4 places. Both magnetos had fragment damage. The propeller hub showed impact marks. The reduction gear housing was cracked. Yet the engine had run for 25 minutes after sustaining this damage. It had produced enough power to maintain flight, enough thrust to keep the propeller turning, enough reliability to bring the pilot home. When maintenance officers disassembled the engine, they found metal shavings throughout the oil system. Bearing material, piston rings, valve components, all grinding against each other in the final minutes. The oil sump was nearly empty. What little remained was more metal than lubricant. Theoretically, the engine should have seized within seconds of losing oil pressure. Practically, it had run for 10 minutes. Engineers from Pratt & Whitney examined the wreckage. They calculated that bearing clearances had expanded from heat to the point where metal-to-metal contact was occurring on every revolution. The crankshaft had been running against bearing surfaces with minimal lubrication. Friction had generated temperatures exceeding design limits by hundreds of degrees. Components had been welding themselves together microscopically with each rotation, then tearing apart on the next stroke. Somehow, enough clearance had remained for the engine to continue functioning. The 18-cylinder radial design had saved it. With 5 cylinders completely destroyed, the remaining 13 had distributed the load. Each surviving cylinder produced less power, but collectively they generated enough to sustain flight. The engine's modular design meant that cylinder failure didn't cascade into total failure. Each cylinder was somewhat independent. Lose one, the others compensated. Lose 5, the others still compensated. The design had redundancy built in at the most fundamental level. This incident became a case study distributed throughout the Air Material Command. Copies went to every fighter group in every theater. Republic Aviation incorporated the findings into design reviews for future variants. Pratt & Whitney analyzed the engine survival and made minor modifications to improve oil retention under damage conditions. But the core lesson was simpler. The existing design already provided extraordinary survivability. No major changes were needed. The aircraft just needed to keep being built exactly as it was. Pilots needed to keep trusting it. Maintenance crews needed to keep repairing it. The system was working. June 1944, Normandy invasion support operations put P-47 squadrons into the most intense combat operations of the war. Ground attack missions against German positions exposed aircraft to concentrated small arms fire and light flak. Unlike high-altitude bomber escort, these missions took place at low altitude where every German soldier with a rifle could shoot at passing fighters. Aircraft returned with hundreds of small-caliber hits. Rifle rounds, machine gun fire, fragments from exploding ammunition and fuel stores. The cumulative effect was perforated airframes that looked like they'd been hit with shotgun blasts. One aircraft returned with over 300 documented holes, most smaller than a dime. Individually, none was catastrophic. Collectively, they should have caused systems failures across the board. Fuel leaks, hydraulic leaks, electrical shorts, control cable damage. Yet the aircraft had flown home. Engineers studying the damage realized that the P-47 system architecture provided survivability through separation and redundancy. Fuel lines ran through different sections of the wing. Hydraulic lines were routed separately from electrical conduits. Control cables had physical separation between redundant runs. Damage to one system rarely affected another. A bullet could sever a fuel line without touching hydraulics. Another could cut an electrical wire without affecting control cables. The aircraft degraded gradually rather than failing catastrophically. This graceful degradation was the opposite of catastrophic failure. Instead of one critical hit causing total loss, the P-47 absorbed multiple hits and continued functioning at reduced capability. Pilots learned to manage degraded systems. Flying with partial hydraulics meant manual gear extension. Loss of electrical power meant no radios but retained engine ignition through magnetos. Fuel system damage meant switching between tanks more frequently. Each problem had a workaround. Each workaround was trainable. Pilots who understood their aircraft systems could keep it flying through damage that looked catastrophic to outside observers. July 1944, a statistical analysis study compared P-47 survival rates against German fighter survival rates in similar combat conditions. The data was striking. When hit by equivalent weapons fire, P-47s had a 73% probability of returning to base. Messerschmitt 109s had a 42% return probability under similar damage conditions. Focke-Wulf 190s had a 51% return rate. The American aircraft was significantly more survivable than its German counterparts. This wasn't due to superior piloting or tactics. It was purely structural. The P-47 could absorb more damage and continue flying. The German fighters, lighter and more agile, were also more fragile. A killing blow to a Focke-Wulf might be survivable damage to a Thunderbolt. The statistical advantage translated directly into pilot survival rates. American fighter pilots in Europe had a 78% survival rate through a standard 25-mission combat tour. German fighter pilots on the Western Front had a 31% survival rate through equivalent operational periods. Multiple factors contributed to this disparity. Allied air superiority, better training, numerical advantage. But aircraft survivability was a measurable component. Pilots flying tougher aircraft lived longer. Republic Aviation's marketing department began using survival statistics in procurement presentations. Charts showed loss rates. Graphs displayed return rates after combat damage. Photographs documented aircraft with extreme damage that had landed successfully. The message was clear. The P-47 brought pilots home. This wasn't empty advertising rhetoric. It was documented fact supported by operational data from 3 years of combat. Military procurement officers reviewed the evidence and approved continued production orders. The P-47 remained in production through the end of the war despite the P-51 Mustang's superior range and speed. Why? Because survivability mattered. A faster fighter that couldn't absorb damage was less valuable than a tougher fighter that brought pilots home consistently. The Air Force chose both. P-51s for long-range escort where their efficiency mattered. P-47s for ground attack and close support where their toughness was essential. August 1944, the advancement of Allied forces across France created forward operating bases closer to the front lines. These rough field airstrips had minimal maintenance facilities. Aircraft operating from these bases couldn't receive extensive repairs. They needed to be tough enough to sustain minor damage and keep flying without depot-level maintenance. The P-47 excelled in this environment. Field maintenance crews developed expedient repair techniques. Aluminum patches riveted over holes. Control cables spliced with replacement sections. Hydraulic lines rerouted around damaged sections. Electrical systems rewired using spare wire and salvaged connectors. These field repairs weren't elegant, but they were functional. An aircraft could take damage, receive field repairs overnight, and return to combat the next morning. This operational tempo was only possible because the basic airframe was robust enough to fly with temporary repairs. A more delicate aircraft would have required depot maintenance for the same damage. The P-47 just needed patches and adjustments. One squadron maintained an operational readiness rate of 87% while operating from a forward base in France. This rate included aircraft with combat damage awaiting repair. Of the aircraft in maintenance status, most were flyable but held back for proper repairs rather than emergency necessity. If needed, they could be launched. This readiness rate was extraordinary given the combat intensity and primitive maintenance conditions. It testified to both the aircraft's durability and the effectiveness of field repair procedures. Maintenance officers documented these repair techniques and forwarded them up the chain of command. Air Material Command compiled a field repair manual specifically for P-47s operating from forward bases. The manual included illustrated procedures for common damage repairs. Patch placement for different damage types. Cable splicing techniques. Hydraulic line repair using salvaged components. Electrical system troubleshooting with minimal test equipment. This manual became standard issue for every P-47 squadron operating in combat zones. September 1944, as Allied forces pushed into Germany, Luftwaffe resistance intensified. German fighters defended their homeland with desperation tactics. Rams, head-on attacks, close-range gunnery that risked collision. P-47 pilots encountered aggressive opponents willing to die to take down American bombers and escorts. In this environment, aircraft toughness meant everything. Multiple pilots reported instances where German fighters had flown directly at them, firing continuously until breaking off at the last possible moment. These attacks created dense impact patterns on small sections of airframe. Instead of scattered hits across the entire aircraft, damage was concentrated on the nose, wings, or tail. This concentrated damage was more dangerous than dispersed hits. It could destroy critical components clustered in one area. Yet P-47s survived these attacks repeatedly. One pilot described a Messerschmitt 109 that fired from head-on range until the German pilot pulled up with less than 50 feet separation. The American pilot saw his own aircraft shudder from impacts. His windscreen starred from a bullet impact. Oil sprayed across the glass. Engine gauges fluctuated. But the engine kept running. Controls still responded. He completed his mission and flew home with 42 holes in the engine cowling, 16 in the nose section, and 8 in the windscreen and canopy framing. The concentration of fire should have destroyed the engine. Multiple cylinders were hit. The reduction gear housing was cracked. Oil and fuel lines were severed. Yet enough cylinders continued firing to produce power. Enough fuel reached the engine to sustain combustion. Enough oil remained in the system to prevent immediate seizure. The aircraft limped home at reduced power and landed safely. The engine was a total loss, but the pilot survived. These head-on attack survivals demonstrated the radial engine's superiority in combat damage resistance. A radial engine presented a circular target from the front. 18 cylinders arranged around the crankcase. Incoming fire might destroy 1 or 2 cylinders, but the others remained functional. An inline engine, by contrast, was more vulnerable to frontal attacks. All cylinders were aligned in a row. A bullet penetrating the engine block could pass through multiple cylinders, coolant passages, and the crankshaft. One hit could catastrophically damage an inline engine. The same hit on a radial might destroy 1 cylinder and leave 17 functioning. This geometric advantage was unintentional but decisive. Republic hadn't chosen the R2800 radial engine for combat damage resistance. They'd chosen it for power output. The damage resistance came as a fortunate consequence. October 1944, pilot debriefing reports began including detailed descriptions of how aircraft handled under specific damage conditions. Intelligence officers compiled these descriptions into handling characteristics references. Pilots learned what to expect when certain components were damaged. Loss of left horizontal stabilizer creates right roll tendency. Compensate with left aileron and right rudder. Rudder damage creates directional instability. Maintain heading with aileron inputs and throttle adjustments. Engine running rough from cylinder damage produces vibration and reduced power. Reduce manifold pressure to smooth operation. Throttle gently to prevent further damage. These handling notes were shared across squadrons. New pilots learned from veterans' experiences. The institutional knowledge base grew with each mission. By late 1944, P-47 pilots understood their aircraft's damage tolerance better than the engineers who'd designed it. They knew what would kill the aircraft and what was survivable. They knew which damaged systems were critical and which were redundant. They knew how to coax a crippled fighter home through technique and determination. This knowledge saved lives directly. Pilots who might have bailed out instead stayed with their aircraft. They worked the problem, applied the techniques they'd learned, and often succeeded in returning to base. Each successful return reinforced the lessons. Each landing with severe damage proved the aircraft's capability. The psychological effect was profound. Confidence replaced fear. Pilots trusted their aircraft because their aircraft had earned that trust through repeated demonstration of survivability. German pilots noticed the change. American fighter pilots were becoming more aggressive. They pressed attacks longer. They accepted damage that should have forced disengagement. They kept coming even when hit. Luftwaffe tactical reports described American fighters as recklessly aggressive. the assessment missed the point. American pilots weren't reckless. They were confident. They knew their aircraft would survive damage that would destroy German fighters. That knowledge made them effective combatants. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.